Okay, Bismillah Rahman Rahim. So today we will continue with lecture number 9, Forces on Immersed Bodies. In the previous lecture, we studied about forces on immersed bodies, what are the different forces that are developed, how we can calculate them, and then we studied about the drag forces in detail. The drag forces has two components, the friction drag and the pressure drag. And after that we studied about drag on three-dimensional bodies. We continue with that, and this topic is drag on two-dimensional bodies. Now in this figure you can see that we have the drag coefficient that is plotted against the Reynolds number. So previously we saw a similar plot for three-dimensional bodies. In this case, for two-dimensional flow, so you can see here the infinite circular cylinder. Infinite in the sense that the length is infinite to avoid the end effects on the flow. So in that case, you can see that the graph of CD versus the Reynolds number, this is very much similar to what we saw earlier for a sphere, three-dimensional flow. Clear? So in this case, you can see that when Reynolds number is less, you see here when the Reynolds number is less in this range, so this CD, it follows this straight line here. And as the Reynolds number is increasing, you see we are moving in this direction here. So it follows this curve, and you can see that after certain Reynolds number, we can see that this curve becomes horizontal. Means that for this range of Reynolds number here, the drag coefficient is almost constant. And then at this point here, above 250,000, for this Reynolds number here, you can see that there is a sharp drop in the drag coefficient. And just like we saw for a sphere, three-dimensional bodies, this is due to change in boundary layer from laminar to turbulent. If you compare here, this was a cylinder that is infinite circular cylinder, means that the length is sufficiently long to avoid the end effects on the flow. But if we consider a finite circular cylinder with length to the diameter ratio as 5, you can see that this is the curve. Below, clear, it means that the drag coefficient, it is less as compared to a cylinder of infinite length. And the reason is that because of the end effects, it will help dissipate the energy, and as a result of that, the drag force will be reduced. So the drag coefficient is small, small is the drag force. And similarly, you can observe for other two-dimensional bodies. Now, whenever a flow passes past this cylinder, which is shown the cross section of a cylinder in this diagram. This is from our textbook. And whenever the fluid flows past this cylinder, so you can see that on increasing the Reynolds number, what will happen that these vortices will form. Another thing to mention here is that you see this diagram is from the textbook. You can see that in the textbook for this diagram, the velocity is denoted by V. So that's why initially I use V to be consistent with denoting the velocity as we have done so far. But as I said before, that when you study this chapter in different fluid mechanics books, including our textbook, they are using U, or they are using U infinity. This is used to denote the free stream velocity, means the velocity with which the fluid approaches the body. So anyhow, just to be consistent, I am using this capital V so that we are consistent in denoting the velocity. So this should be clear to you. Now, when this fluid flows past this cylinder of diameter d, you see when the Reynolds number increases, means that this velocity increases, so these vortices will form. There is a backflow, you can see here, the liquid flows in the backward direction, swirling in a rotation, and similarly on the other side also. We will later on discuss that what are the reasons for this. So these vortices will form, and then what will happen, that these vortices will shed. You can see here this vortex shed from this cylinder, and it moves in the downstream direction, means on this flows towards the right direction, clear, to our right direction. So you can see that these vortices, they will shed from this body surface and then continue to flow in this downward direction, downward or downstream direction, we can say, after the flow passes. So you can see here that first this phenomena will occur on one side, and then it is followed by the other side, clear. You can see here these vortices will form, and they will shed from this body and continue to flow with the fluid. So this arrangement, these are the approximation given, that the distance between the two is 1.2 times the diameter, and so on. So this shedding of vortices, they will form what is known as Kármán vortex street. This is known as Kármán vortex street. So von Kármán, we earlier used his contribution in pipe flows also for friction factor. In this case, this Kármán vortex street, that is following a cylinder, clear. And in this case, since the fluid is swirling and flowing, so the velocity of eddies, these eddies which will form packets of fluids, so VED is less than the velocity of the fluid. So this will happen, clear, when a fluid passes a cylinder and the velocity is increased, these vortices will form and these vortices will shed, clear, after the fluid flows past this body, for example cylinder in this case. So this is important phenomena, clear. Why we are interested to study this thing? You can see that this alternating shedding of vortices and the accompanying forces give rise to the phenomena of aerodynamic instability. So what happens when this type of situation occurs? This contributes to what we call as aerodynamic instability. And this phenomena is very much of importance in the design of tall smokestacks. Tall smokestacks means, for example, the chimney, where we have a cylindrical structure and from the top you release the smoke. Like we have chimney in our department also, you might have observed such type of structures. Tall smokestacks and suspension bridges, because in suspension bridges the wind, it flows past the components of suspension bridges. So this phenomena, this what we call as Kármán vortex street, this is known as aerodynamic instability, and this is very much important in the design of these structures. Tall smokestacks, because cylindrical shape and the wind flows past it. Similarly, suspension bridges, we have cables, etc., other components, and the wind flows past these structure or structure components, so it will give rise to this type of phenomena. And also we understand it to account for singing of wind blowing across wires. Clear? So coming to this thing, before we discuss that why this is important, you can see here the formation of these Kármán vortex street. Here you can observe. You can see here the flow occurs around this two-dimensional body, and you can see the formation of vortices. So this frequency at which the vortices are shed was first given by G.I. Taylor and substantiated by Lord Rayleigh to be about this, given by this equation. The frequency with which these vortices are shed, this one, these vortices which are shed after the fluid flows past the body. And this is very important, as we can see that we civil engineers are concerned with this, because you see tall smokestacks and suspension bridges. So the frequency at which these vortices are shed, that was given by Taylor and substantiated by Lord Rayleigh to be about, given by this expression. Frequency will be equal to 0.2 times V by D, velocity by diameter 1 minus 20 by R. R is the Reynolds number. So we know all the parameters. Clear? And why we are interested in this? Because a serious condition can result if natural frequency of vibration of structure is equal or close to the frequency of the shedding vortices. So this is written in your textbook. It says that if the frequency of vibration of structure, which you might have studied suspension cables and bridges also in your structure course, or study about that in physics at the school or college level. So same we deal here. If the natural frequency of vibration of structure is equal or close to the frequency of shedding vortices, then this will result to a serious condition. Clear? Because we already studied that this phenomena, this is known as aerodynamic instability, and we consider them in the design of these structures. Next, we study about the lift. So far, we studied about drag. We calculated the drag. We studied drag on two-dimensional and three-dimensional bodies. Next, we study in detail about the lift. So lift we already defined in the previous lecture. Lift is a force that acts on an immersed body normal or perpendicular to the relative motion between the fluid and the body. And the lift coefficient is expressed as given by this equation. So this we already discussed, the lift coefficient, which is represents dimensionless form of the lift force. You can see here this is a ratio of two similar quantities, so no units. FL divided by half rho V square A, and A is the characteristic area that we are defining. It is the projected area in a plane perpendicular to the force vector. Clear? And rho is the mass density, V is the velocity. So this lift force, this is a force which acts on a immersed body perpendicular to the relative motion between the fluid and the body. So the most common observed example of lift is that of airplane wing supported in the air by this force. We already discussed, and I show you this picture in the previous lecture, that when an aeroplane flies through the air, so definitely it has the weight which will be acting down towards the center of the earth, and the engine of the aeroplane, it pushes the aeroplane in the forward direction by applying a thrust. And because of this motion of the aeroplane through the air, two principal forces that are developed. The first one is the drag force, which is parallel to the direction or relative motion between the fluid and the object, parallel to that. So that is the drag force. And we studied that initially it is a resisting force. It resists the motion of the body. And in addition to the drag force, another force is developed in a direction normal here, normal or perpendicular to the relative motion between the fluid and the body. And this force is known as the lift force. Clear? So in this case, the commonly observed example in aeroplane, etc., flying objects, the kites that we fly kites during childhood, or even later than that, we are interested to fly kites. So this lift force exerted on a kite helps the kite to fly in the air. So similar objects, airships, etc. So in that case, this lift force, you can see here it is perpendicular, and because of this lift force, objects are able to fly in the air. So this is the very common example. So it's not that this lift force is always developed when we have this aeroplane. Remember, when we have a car that we commonly use for transportation, etc. So in cars also lift forces will develop, but we design the car shape in such a way to minimize the lift so that the contact between the tires and the road that is intact. So but in case of aeroplanes, etc., because we want to fly high in the air, the lift force is of much importance and we want to maximize it. Clear? So in this case, you can see that when the fluid it approaches a body, and this body here, which is shown here, this is the shape it approaches with a velocity v, as we already discussed. This is known as airfoil. Clear? This is known as airfoil, a general term which is used to denote by this, because if you cut the wing of aeroplane, the cross section will appear like this. So in this case, you can see that when the fluid approaches and flows past this object here, so you see these two forces are developed, the drag force, which is denoted by Fd, and the lift force, acting perpendicular to the direction of relative motion between fluid and the body. So now in this lift force, you can see here that when you calculate this lift force, if we know the lift coefficient, it will be equal to lift coefficient multiplied by this half rho v square into A. So as I said that this A is actually the characteristic area. So now in this case, it is just the area projected on a plane that is perpendicular to the force vector. So you can see that for the lift force, it will be the plane form area. What we mean by the plane form area, if you look to this object, so it has this span B, but on this side, you can see this is the curve. So what dimension we should use? We use this chord C. And if you look to this plane from the top, what will appear? It will appear as just this dimension to you, multiplied by this dimension, span. So that's why this is the plane form area, and it is given by simply B by into C, B into C, the plane form area. Okay? So normally, remember, what we do is that for this area, even in case of drag forces, we just consider the projected area on a plane that is perpendicular to the force vector, either the drag force or the lift force. So this is important, characteristic area. Now in this figure, the other important thing is that this chord here, you already know from mathematics what is chord. So this chord here, which we join these 2 points here, it makes an angle with the horizontal. Any point you draw horizontal, it makes this angle, and it is denoted by alpha, commonly in fluid mechanics books, and this is known as angle of attack. What is angle of attack? This is just this chord makes an angle with the horizontal axis, and this is very important parameter in the design of these objects, as I will show you later on in this lecture. This angle of attack is very important parameter in the design of these objects. So now we know that what is a lift force, how it can be calculated. Now we study the mechanics behind this lift force, that how these lift forces are developed on immersed bodies that are moving through the fluids. So in that case, we talk about lift and circulation. You can see here in this diagram, which is from your textbook. So here, this point is known as the stagnation point, because stagnation point in the previous lecture, when I discussed about the static dynamic and stagnation pressure. So stagnation point means that where velocity is zero. So in that case, pressure will be maximum. Clear? This is what we follows from the Bernoulli's theorem. Now this chord shape is such that it is cambered for airfoil. So this is again what we do is that if you take a section here, so this is how this appears, the shape that we commonly consider airfoil. And again the chord C, it makes an angle alpha, this is angle of attack. So now these diagrams are shown for alpha is equal to 8.6 degree. Clear? Now what happens is that this fluid, it is approaching this with a velocity v. You can see here these vectors of the velocity. So these are the streamlines which are shown, and this fluid, it will flow past this object. You can see here at the top, the spacing of the streamlines is less, the spacing between, but here the spacing is more. So we get some idea from here that what is going on. The idea that we get from here is that when the streamlines are close to each other, what we can say is that here at the top surface of this airfoil, what we can write down here is that V increases. Clear? V increases. And here at the bottom, what we can observe is that V decreases. So I will explain later on that why this happens. I will explain in detail that why this happens. So now that from this diagram we can see that velocity increases, and at the bottom surface of this object velocity decreases. So according to Bernoulli equation, if velocity increases, then what should happen? Pressure P should decrease. If velocity increases, then pressure should decrease. And here at the bottom, what will happen? That pressure should increase. So when this happens, so this gives rise to this part B pressure distribution here. You can see the pressure distribution diagram on this object in this figure B. So what happens that pressure decreases, that's why you can see that at the top we have negative pressure on the upper surface. And you see at the bottom or lower surface of this foil, you can see that pressure increase, so positive pressure on the lower surface of foil. So because we have this negative pressure here and a positive pressure here, we already studied that flow occurs from high energy area to low energy area. Clear? So that's why, because we have high pressure here at the lower surface and low pressure at the upper surface, so there will be a tendency that a net force will be created in the upward direction. Because of this pressure difference, if we do not have pressure difference, there will be no force acting. So because of this pressure difference, in this case there will be a net force that will be developed in the upward direction. Since it is normal or perpendicular to the relative motion of the fluid and the body, so we call it as the lift force. Clear? But this is not always the case. Remember, if the object shape is such, we already discussed the effect of shape on forces that are acting on bodies immersed in the fluids. Remember, very important. So if it happens that we have more pressure, it means that we have high pressure here. Let's say if we have a case, it is possible you modify the shape, and we have low pressure at the here. So then in that case, this force will be acting down. So this is not always that we will have this. This depends on the shape of the body and flow conditions. If we have a high pressure at this point here and a low pressure here, then the force will be acting in the downward direction. I will give you examples for this also later on in this lecture. So now that we know that there is increased velocity and decreased velocity which affects the pressure variation on the top and at the bottom surface, and because we have the pressure difference, so you can see that a net upward force is acting on a body. This explains that how this lift force is developed on these bodies. So now we understand what is the lift force and how the lift force is developed because of this diagram that we can see that this results into development of this force. Now the next question is that why the velocity increases at the top surface and the velocity decreases at the bottom surface. Now we come to explain why this happens, that this gives rise to this pressure distribution diagram, and because of this it results into this net upward force acting on this body. So to explain this, this is another diagram which is also from your textbook. You see here that in part A of this figure, you can see that the fluid, it approaches this body, clear, with a velocity v. So this is uniform rectilinear flow field, means you can see all the velocity vectors, they are parallel to each other and one dimension. So rectilinear flow field, and on the object there is a circulation. Clear? On the object you can see there is a circulation. So when this fluid, it flows past this object, so what will happen is that you see that, let's say this will follow this direction here, similarly this will follow this direction. Just for understanding here, let's say this follows this direction here and this follows this direction. This is just for understanding, let us assume. So now what happens is that there is a circulation and now the fluid flows past this object. So you can see that both the velocity vectors here and here, they are in the same direction. So they add up. So you can see here the vectors, they add up. So that's why this result into V increases. This is the reason that V increases at the top of this object. And at the bottom you can see here that the approach velocity of the fluid, it is opposite to this vectors of circulation around this body. So definitely what will happen that at the lower surface of this object, what will happen that V will decrease, because these are opposite directions, so they will decrease. So now velocity decreases here as a result of this, and velocity increases here at the top surface, and that's why you can see that the velocity is increased, shown by large size of vectors here. V increases here, you can see, and small vectors here, you can see that the velocity decreases at the lower surface of this object. So now we understand that why velocity increase and decrease, and now we can understand that because of this increase velocity and decrease velocity we have pressure change, and because of the pressure change we have this force which is developed on the body. Clear? So now the next question then comes that from where this circulation comes. Now the next question that we want to answer is that, okay, that there is a circulation and there is a relative motion of the object and the fluid, and because of this velocity when it comes here it will further increase the velocity, and here at the lower surface it will decrease the velocity. It will result into difference of pressure at the top and bottom, and it will give rise to this force acting on the object. So now the next question is that from where this circulation comes. Okay, we understand that the fluid approaches the body with a velocity v. So from where this circulation comes. So to understand this is another sketch which is again from our textbook. You can see that when the fluid leaves the object at the trailing edge, you can see here that there is velocity discontinuity at the trailing edge. This point is known as trailing edge, and this front portion of the body, this is known as leading edge. This is known as leading edge. This terminology you will come across when we solve the problems. You will be asked that what is this parameter value at the leading edge, at the trailing edge. So just remember that this is the trailing edge and this is the leading edge. So you can see velocity discontinuity at the trailing edge. Because of the difference of the velocity vector, there is a vortex which will generate. We already saw the vortices. So there will be a vortex generated as this fluid leaves the body. That's why we studied here. This is very important concept. Clear? You can see here, this we earlier observed. When the fluid leaves the object, it flows past the object, these vortices will form, and then these vortices are shed and they will travel in this direction. So same concept here, that when the fluid leaves here, because of velocity discontinuity, this vortex will generate. So you can see that as a result of this vortex generates, let's say, in this counterclockwise direction here. Since the object that is in equilibrium, so if you consider a frame of reference, so the net circulation must be 0. And this circulation is denoted by capital gamma. This notation that we use, that is the capital gamma. This is used to denote circulation in our textbook. So the net circulation, that should be 0. For this, let's say the counterclockwise vortex, this is the starting vortex, and this is true for the objects because I show you the video. So we cannot say that this is imaginary, something imaginary. I show you the video. These vortices are generating. See the Karman vortex street. I show you video of this. So these are actually happening. Clear? It's not that these are imaginary. So what happened is that there is this counterclockwise vortex. Now to balance, so that the net circulation is 0. To balance this one, there must be a clockwise rotation on this body. So we have this anti-clockwise and this is an clockwise rotation. This will result into net circulation is 0. So when we have this situation, we can say that this vortex, it will shed. So that's why it will shed from this body after passing, it will shed. So this is that counterclockwise. This is the rotation, and for net rotation to be 0 in a frame of reference, so you can see that there will be this rotation around this body. It will result into this rotation around this body. So this explains that how this rotation, or we can say circulation, occurs around this body, and then this body is here for this circulation, and when this body moves and the velocity of the fluid approaches this body, it will result into increased velocity and decreased velocity, and this will result into increased pressure and decrease pressure, and it will result into this force which we are interested to calculate. So now in this case we try to understand the mechanics behind that from where this circulation comes. And remember, this circulation will be on the body as the body moves. For example, this can be the wing of aeroplane. So when the aeroplane starts motion, this circulation will develop, and when it moves through the air, it will result into this velocity difference and then pressure difference and then the net force that will be developed. If the aeroplane is at rest, then there will be no circulation. This circulation will only develop when there is a motion. So that's why when the aeroplane is standing, we cannot expect that a lift force will be developed and it will go up in the air. So when the body moves, then this happens and it will result into this circulation, and this circulation, when the object moves through the air or fluid, and it will result to increase or decrease velocity, and it will result into increase or decrease pressure, and as a result of that this force is developed. So this is the mechanics behind how this force is developed. Now before I said that in these lift forces, this angle of attack, this is very important parameter, and this angle of attack which this chord C, it makes with the horizontal. The angle that this chord makes with the horizontal, this angle is known as angle of attack, and this is very important parameter, clear, because it affects directly the lift force. This is what you can see here in this diagram. So when we let's say the angle of attack is 5 degree, so you can see here this is the chord that we denote here, this is the chord, and with the horizontal axis it makes this angle as alpha, which is angle of attack. So this angle of attack, it is 5 degree. You can see here that on this object the drag force and the lift forces are developed, that we already discussed. Now we know that how these forces are developed, how we can calculate them. When you increase the angle, this angle of attack, you can see that the drag force is increased. You see here the size of the vector is greater than here. So if this is 15 degree, the lift force is increased. Should we increase it more and more, the lift force will increase? This is not the case, because it says that after reaching some limit or range, beyond that if we further increase the angle of attack, you see here it is 30 degree here. This is, for example, the chord here, and this is the angle of attack, and this is 30 degree. So then in this case you can see that as compared to 15 degree, the lift force has reduced. It has reduced and the drag force has increased. So that's why I told you that this angle of attack is important parameter in the design of wings of aeroplane and similar objects. So the thing is that how we determine these angle of attacks, 5 degree, 15 degree and 30 degree. So if you study books on fluid mechanics, they will say that a large number of experiments were conducted by NASA, clear, the National Aeronautics and Space Agency in the America. They conducted large number of experiments in the 1930s and around that. And because we at that time were designing the aeroplanes, so they conducted large number of experiments to come up with the optimum values for this angle of attack, so that the drag force can be kept as minimum and the lift force can be increased as we want to fly the aeroplane high in the air or similar objects, clear. So you can see that if the angle of attack is greater than 15 degree, which is shown here, flow may separate completely from the top surface of an airfoil, reducing lift drastically and causing airfoil to stall. So this is important, clear, in the design of airfoils, etc. Before I further discuss on this, so you can see here, now you see that we are increasing the angle of attack. You can see here that reverse flow will occur. I will explain this later on in the detail. And the point of separation, it goes up, forward. So if we further increase angle of attack, so you can see it will result into reduced lift, and the drag force will increase in this. Next, we discuss about the boundary layer theory. So the boundary layer theory, this we already discussed in pipe flows also, internal flows, and the boundary layer that develops clear and then merges at the center, and we have the velocity profiles in case of laminar and turbulent flows. So also we have this concept in external flows. Before we discuss, this is very important concept when we study external flows. So this D'Alembert, I talk about this, I think, in my first lecture. He was a mathematician in the 18th century. So you can see that previously what happens that we try to calculate the resisting forces. So as I said that we deal essentially the fluid as ideal, frictionless. We apply mathematics and study the flow phenomena. So if there is no friction, zero viscosity, so there will be no forces acting. So what happened at that time, D'Alembert, he applied the theory, and this is how the streamline is shown here. This is an elliptical body. You can see here the shape in the form of ellipse, elliptical body shape. And these are the streamlines, they flow past this body. So in this case, when you apply the theory and you do not consider the friction, then how you will be able to calculate the force acting on this body? Because we already know when you move through the fluid, resistive forces will be acting. We want to calculate at that time, we apply the mathematics and we consider the fluid to be ideal. So then how we calculate the resistive forces? This was a question at this time. So D'Alembert, he said that I do not see, I admit, how one can satisfactorily explain by theory the resistance of fluids. So he said that I do not see how one can explain by theory resistance of fluids. On the contrary, it seems to me that the theory in all rigor gives in many ways zero resistance. When you apply the theory to calculate the resistance, you get zero. So how to calculate the resistive force? I know there is a resisting force, but when I apply the theory, I get zero result. So this was known as a singular paradox. This was known as D'Alembert paradox at that time, which I leave to future geometers for elucidation. So D'Alembert said that I apply the theory, but I get zero resistance. So he said that this is a paradox. We do not understand what is happening. So he said that my knowledge is not sufficient at this time, and I leave this problem to the future people, future geometers, scientists, engineers, for elucidation, for clarification, to explain why it is like this. So this was around this time here. Then in this time, 1904, earlier 20th century, you can see that the geometer who provided the clarification was Ludwig Prandtl. So he gave the concept of what we know as the boundary layer theory, which is very significant contribution in modern fluid mechanics. And I said in the first lecture giving introduction about fluid mechanics that because of that, Ludwig Prandtl, a German engineer scientist, so he is considered as the father of modern fluid mechanics because he gave this concept of boundary layer theory. He said that there is a very thin fluid layer near the body surface in which viscosity is dominating, resisting forces are developed, and that explains how resistance to flow occurs. Clear? So this was very significant contribution, and this is what we know as the boundary layer theory. So this is how it came into being. Now, before we study what is the boundary layer theory, as I said that we also have the same concept for internal flows. So in case of internal flow, we already studied entrance length, developing pipe. So you see that here the velocity profile is changing, and these boundary layers, they develop, and here they merge. So in this case, then we have fully developed flow, and the velocity profile is fully developed. So internal flows are dominated by the influence of viscosity throughout the flow field. Clear? For external flows that we are studying in this chapter, viscous effects are limited to the boundary layer and wake. For example, you can see here this is a tennis ball, and this is how you can see the streamlines. They are moving around this object and so on. So you see that this airfoil here, the boundary layer, it will start from here and it will be in this wake region. The viscosity effects will be there. The viscosity effects will be there in this region. You can see here the boundary layer that is developed. So on the airfoil here, this is the boundary layer, very thin layer. You can see here that it says that the viscous effects are limited to the boundary layer and wake. This is wake. This is wake. Clear? So here we will consider the viscosity of fluid that plays important role. It is limited to only this region, which is shown color. So outside this region, you see the vectors are equal. It means the velocity is uniform. Even here, outside this boundary layer, the velocity is essentially treated as uniform, or we can say that the fluid is considered as ideal outside the boundary layer. This is the difference between the internal flows and external flows. That in internal flows are dominated by influence of viscosity throughout the flow field, but in external flows, viscous effects are limited to only boundary layer and wake. So it means that outside the boundary layer, the fluid will be treated as ideal fluid. Remember this. So you can see that when this fluid flows past this object, which is shown here in the form of ellipse here, so what happens that you can see that this curve, this is developed. This is known as the boundary layer. And you can see outside this curve, you see it is curved. We have the velocity gradient, just like you studied in case of Newton's law of viscosity earlier in fluid 1 also and in pipe flows also. You can see that outside this boundary layer, you see here velocity is uniform. See, the two lines become vertical. Velocity is uniform. Any point you consider, velocity is uniform. But in this curve, in this region near the surface of the body, you see curve. See the curve. So if I consider one curve, this is what you see here on a flat plate. Although this is a curved body, this is a curved body, but on a flat plate, we can see here that we have a uniform velocity approach, But because this fluid flows past this object, you can see here that at this point on the surface, this is known as the zero velocity at the surface, which we call it as the no slip condition, because the fluid which is in direct contact with the surface will be brought to rest due to the resistance, and then the resistance will be transferred to the other layers, and this results into this velocity profile here, because the resistance will be transferred in this direction. And this diagram is on the top of this flat plate. It is on both sides. Here in this chapter we will study many concepts, but you see we consider this flow on the top surface. It doesn't mean that we do not have this situation on the bottom surface. No, we have similar situation at the bottom surface also. The same lines will be extended here. So it means that if we have this flat plate and we have this velocity gradient and then it continues, clear, it is on both sides. So we just show it on one side for understanding, no need to show it on both sides. And then it is like this. This will be on the other side also, clear. This will be on the other side also, like this. So that's why, just for understanding, we show it only on one side. So now this is the zero velocity, and then the resistance will be offered up to certain level, and then beyond that you can see the velocity vectors are uniform. So essentially the flow behaves like ideal flow, means there is no resistance. So the no slip condition, a fluid in direct contact with a solid sticks to the surface due to viscous effects. Responsible for generation of the wall shear stress. Because of this velocity gradient, we have the wall shear stress that is generated here, and this is what we studied in the pipe flow also, tau naught or tau W. In some books it is denoted by tau W, in our book it is denoted by tau naught. The wall shear stress that is developed because of this velocity distribution diagram, resistive forces that are developed. And this is how the drag force that we studied, you integrate for the entire surface, we can calculate the surface drag force and development of the boundary layer. So the fluid property that is responsible for all this, the no slip condition, and important in the boundary layer, that is the viscosity. And this concept which I'm trying to explain, this is very important boundary condition in formulating initial boundary value problem for analytical and computational fluid dynamics analysis. So as I said earlier, a very brief, maybe in pipe flows chapter, I said that what we do right now is that a new field in fluid mechanics has emerged, which is known as CFD, computational fluid dynamics, where we are using analytical techniques, clear, to solve the complex fluid flow problems due to high-speed computers that are available to us. So this field is known as computational fluid dynamics. So in that case, when we study complex flow problems, in that case, these concepts, boundary layer theory that we are learning, they are important and act as important boundary condition in formulating initial boundary value problems there. So computational fluid dynamics is a specialty in itself. It has become an emerging field because nowadays we have powerful computers available, so we can simulate very complex flows which before were not possible to study. Anyhow, so this is very important concept, boundary layer theory. So to continue with that, this boundary layer theory, you can see that this is a flat plate, same plate that we show here. This is a flat plate, and you can see here the boundary layer develop on both sides. This is what I said, but mostly we only show this top portion in the problems or in the theory that we explain. So we say that, okay, this is the boundary layer that is developed here, and it will continue like this and go till end. but we do not show this portion here. So it doesn't mean that we do not have this situation at the lower. No, we have here also. But in the diagrams in that we try to explain, we only show this upper for understanding purposes. So remember this, it will be on both sides, not just the upper side. Clear? So you can see here in this figure. Now in this you can see that this boundary layer develops. So it means that within this boundary layer we have viscosity effects and we have the velocity gradients that will result. And outside this layer you see the velocity is uniform. You can see here the velocity is uniform. So that's why within this region we have viscous flow. But outside this region, the boundary layer, we say that it is inviscid, non-viscous, zero viscosity, inviscid flow region. The fluid will behave as if it is ideal. So how this develops? This actually develops. If we are able to see this boundary layer, this actually develops on the bodies. Clear? You can see here. So you see that this boundary layer, this actually develops when the flow passed, this case, flat plate. So we consider flat plate because it's very easy to understand the mechanics of the boundary layer, and because later on we are going to develop different equations, so it's very easy to do that. But this will be for all type of objects. If we have a curved object, then it will be complex. So that's why we consider this flat plate commonly in developing the basic concepts. So now you saw that what is a boundary layer. This is important concept, and you already saw in the previous slide that this boundary layer develops. Now we come to see the big picture. So in this case, the big picture is that the same concepts that we studied in pi flow appear here. That the boundary layer can be a laminar boundary layer, or it can be a turbulent boundary layer, or it can be a transition regime. It can be a transition zone here. So it is also possible that we can have the entire boundary layer as laminar. For example, this will continue and it will continue like this. So this entire will be laminar. It is possible, depending on the flow condition. It is possible that the entire layer can be turbulent. It is possible that the entire layer can be turbulent, because practically, as we saw in the pi flow chapter also, flows are turbulent flows. Clear? Laminar flows, these regimes are very rare in practice. Although we have examples for this, but they are very rare. But turbulent flows are more commonly observed. Same is the case here. You see the boundary layer surrounding sea-going ships, submarines, airplane wings, and airships are mainly turbulent. So that's why, but we have to study both to understand the mechanics of that. So you can see that the fluid, it approaches this flat plate and the boundary layer is shown on one side. So it doesn't mean that on the lower side there will not be boundary layer. No, there will be a similar situation here. Like this. But as I said, we just show it on one side for understanding purposes, and we do not draw it on the other side. But there will be on the bottom surface also this same situation here. So now in this case you can see that the behavior of a fluid element, if we have undisturbed flow, you see that the fluid particle element that we consider here, it just moves in a similar fashion here at the top. Means there is no rotational effect, no change in the shape, no deformation. That's why we say that the fluid outside this boundary layer is treated as inviscid flow. But as this fluid element enters into the boundary layer, because of the difference in the velocity, you can see the velocity gradient. So there is a difference of velocity between the two layers. That's why it results into rotation or twisting, whatever you call it, or change in the shape of this element. So in the laminar flow, still the molecules, they are moving in straight lines, just shift from one layer to another to transfer the momentum. But you can see here, the moment this element comes in turbulent boundary layer, you see very irregular path. And this is characteristic of turbulent flow, complex flows, as we studied in pipe flows also. So you can see the behavior of the fluid element when it is in a turbulent boundary layer. So you see complex situation as compared to laminar boundary layer situation. Earlier in the pipe flow, we treated the velocity in a laminar flow can be modeled as in one dimension. But when we come to the turbulent flows, it was essentially three-dimensional flows. That makes the situation complex. Same is the situation here. Now that we understand what is the boundary layer, and it can be a laminar boundary layer and it can be a turbulent boundary layer. So this is the diagram which is from your textbook. But in this diagram, I still continue to denote the velocity with V. In your book, it is denoted by U. And later on, it is denoted by V in other topics. So let us be consistent. I still, instead of U, I denoted with capital V. This is just to be consistent and use one notation for velocity. So now in this case, what you can see that this fluid, it approaches this flat plate. This boundary layer develops. This is the boundary layer. Laminar up to here. Then we have transition. And then we have the turbulent. And same will be on the lower side. It's not that it is only on the top side. No. At the lower side, we will have this situation. But just for understanding, we show it on one side. So in this case, you can see that we have this velocity gradient, and x is the distance from this edge. This is known as the leading edge. This is known as the leading edge. Remember, this you will face in problems, that what is this parameter at the leading edge, and this is known as the trailing edge. Endpoint, this is known as the trailing edge. So now in this case, we can see the velocity distribution diagram for laminar and turbulent flow, and the same concept applies. Even we have transition zone and turbulent zone, there will be a thin layer which will be near the surface of the body, and that is known as the viscous sublayer. The same concept as we studied in the pipe flows. So now in this case, now we understand that what is the boundary layer. Now next we are interested, you see that we have laminar and turbulent boundary layers along a smooth flat plate. This boundary layer, it is very thin, as you saw in the video also, in the previous slides also, but it is shown exaggerated, means the vertical scale is greatly exaggerated. So just for understanding, to visualize, we show it big. Otherwise, this is very thin layer. Clear? So in the laminar zone, the wall shear stress, that is decreasing with x. Clear? Because the resistance is transferred up and up to the outer side. And you can see that in turbulent flow, then the shear stress is more than the shear for laminar. but it decreases slowly with x. So this we study in detail. Now in this case, you can see that for this boundary layer, now we are interested to calculate that what is the shear stress at any distance x. What is the shear stress here? 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 And so on. Because we want to calculate the friction drag forces. Similarly, we are interested to calculate what is the thickness of the boundary layer at any distance x. For example, what is the thickness of boundary layer? It is denoted by delta. So this boundary layer, a very thin layer of fluid adjacent to surface, in which viscosity is important, and considering fluid outside this layer as frictionless or ideal. So now this boundary layer thickness that we will be interested to calculate in problems, the shear stress, the thickness of the boundary layer, the friction drag forces, this we are going to calculate. And we use this boundary layer theory to arrive at those equations. So what is the thickness of the boundary layer? It is the distance from the surface of the body to a point where the velocity is 99% of the undisturbed velocity. What is the undisturbed velocity? This is the undisturbed velocity. Because outside this fluid, you see the velocity is v. But at the surface, at this point here, you see at this point here, the velocity is 0.99 times the free stream velocity. Because if it becomes v, then it is the free stream velocity and the fluid is ideal for that. So the effect can only come up to 0.99 times the v. So this is a definition which is adopted and given in fluid mechanics books. That what is the thickness of the boundary layer in laminar flow or in transition flow from the surface to the point where the velocity is 0.99 times the velocity of the free stream. Because above that we have full velocity, so that is undisturbed. Because 0.99 v and below we have this velocity gradients and the boundary layer effects are there. So this is how we define the thickness of boundary layer, that the distance from the boundary layer to the point where the velocity is 99% of the undisturbed velocity. So this thickness increases with the distance from the leading edge of the surface. You can see here it is 0 here, and then it is ever increases as we move towards the trailing edge. You can see the thickness of the boundary layer. So now we are interested to calculate, how can I calculate the thickness of the boundary layer? How can I calculate the shear stress? How can I calculate the friction drag on this surface? This now we are interested. That's why we study this boundary layer theory. So for this case, before I come to there,
Break, sir.
okay, just give me 2-3 minutes. So we have the laminar boundary layer here, and we have the transition region, and then we have the turbulent boundary layer here. So you see that in case of boundary layer, the critical Reynolds number, that is 5 into 10 power 5. This is the value adopted. That the critical Reynolds number at which the flow changes, the boundary layer will change from laminar to transition and fully turbulent, that is considered as 500,000. This is the value used for external flows. So the boundary layer, it will change in this case 500,000 and then to turbulent boundary layer. Clear? So in this case, what we see is that we can calculate this critical distance at which the boundary layer will change from laminar to transition, or we can say turbulent. So how we can do it? That RC, which is the critical Reynolds number, this one, RC, divided by R, which is the total Reynolds number for the entire length L. For the entire length L, because we say R is equal to V into L divided by nu. So this will be the entire, and RC will be at a distance xc. At any distance x, what will be R at any distance x? That will be equal to V into x into nu. You can see here, when we use R, it is for the entire length, but Rx at any distance x. So that's why RC by R is equal to XC by L. So then we can calculate this XC. R is known, L is known, RC is 500,000. We can calculate the distance at which the boundary layer will change from laminar to transition or turbulent. Clear? So you can see here the thickness of boundary layer. Now we have a moving plate. You can see a plate is moving at the bottom, and you see the boundary layer that develops, increases in thickness, and this delta we are interested to calculate. This is the boundary layer effects that comes. So now we are interested to calculate the thickness of the boundary layer. That what is this delta at any distance x on this body.